now that we established how to write the equation of a line and we've done different questions about them, we now want to see the relationship between two lines or three lines, for example. We've done some similar questions in the previous lesson, but now we're going to dive a bit deeper. So line properties, if we have two-dimension lines, then I can say that the lines are, they could be parallel or they intersect at a point. Now, once we move into 3D, which is hard to imagine with this diagram, but let's imagine this is the 3D diagram here. So the lines can have three different properties. They could be parallel, so this could be line 1 and line 2. If you see here, they're parallel. Two lines can intersect at a point, so you can see L3 and L2. So this is L3 and L2. Or they could be skewed. So skewed is, they're neither parallel nor they intersect. So if you think about them in 3D, they're, from the word itself, they're skewed. So they don't meet these two conditions. They have no equal or collinear direction vector. So an example here would be line 2 and 4, which is hard to see. It feels like they're in 2D, but that's what we call skewed lines. So how do we solve these questions? Well, there's a nice procedure or a checklist that you want to go through. So first of all, you check the, this is the direction vector. You can avoid calling it B, you can call the direction vector. If you have two lines and the direction vectors are parallel, which means they are multiples of each other, then the lines would be parallel. So, and as well, if they have at least one common point, so if they meet this condition and a common point, it means they coincide, which means they're actually the same line. So that's the first checklist you go through. First, check if the direction vectors are parallel. If they are, you check if they have a common point, then they coincide. If they don't have a common point, then they're just parallel lines. Now, if this doesn't work, let's say this is not, they're not parallel. So then you go to the second part. You set the two equations to be equal to each other. So just like you would do when trying to solve, when you have two equations in gradient intercept form and you're trying to find the point of intersection, you make them equal to each other. Same thing. You make the two lines exactly equal to each other. You will get a system of three equations in this case. So if you're in 3D, we're talking about 3D in this situation. So if you're in 3D, you get a system of three equations where if lambda is your scalar for R1 and mu is your scalar for R2, you get three equations for lambda and mu. Now, technically, you only need two equations to be able to find the value of lambda and mu. So what the three equations are useful for is, first you're gonna consider solving for lambda and mu. You can consider the first two equations, but in reality, you can take any two. Sometimes you'll notice the third one is more helpful and so on. So you pick two equations, you find a lambda and mu. Once you find a lambda and mu that would fit the first two equations, you check, does it fit that third equation that you have? If the values that you found do fit the third equation, then we say that the lines intersect. Okay, and once you've confirmed that they intersect, if the question doesn't require anything further, that's it. You just say the lines intersect. If they want the point of intersection, then the lambda and the mu that you found, you just substitute either lambda in your first line, because that's where it belongs to, or you can substitute your mu into the second line, and they should both give you the same point. So that will give you the point where they intersect. Now, if the lambda and mu you found here does not satisfy that third equation, you get a contradiction somehow, then we say that the lines are skewed. So you've gone through this checklist. It's neither parallel nor intersecting, so they have to be skewed. So you have to go through this process. You can't try and prove they're skewed and then suddenly realize that they're actually parallel. So go through this checklist. It's a nice and simple method to follow. We're just going to do two example questions. They can be approached differently, obviously, as long as the algebra that you're doing is correct. You don't have to specifically follow my method step by step. but at least going through this checklist is very important. So let's just have a look at this. I have two lines and I need to show that they are skewed. So first, before, I know they told me they're skewed, but I need to show that it doesn't fit the other criterias. I'm going to write this in vector form because it's going to be easier to look at. So I'm going to call the first one R1, and it's going to have the vector form x, y, z is 1, minus 2, 0, and 3, 2, and 1. And the second one is going to have a minus 3, 0, 2, and then mu, minus 2, 3, and 4. Obviously, lambda and mu are real numbers. And you can immediately see that 3, 2, 1 is not parallel. So they're not scalar multiples of each other, 2, negative 2, 3, 4. So the lines are not parallel. So that's something we write to the side. You can add more details. I'm avoiding details just to save up space here. So what do we do next? The instruction was to make these two equal to each other. So I'm going to take this part and this part. We make them equal to each other. So, and I'm going to write it in equation format. So in parametric format. Remember, parametric format is when you take the full thing here. So x is equal to 1 plus 3 lambda. Well, this is also x equals to negative 3 plus minus 2 mu. So I'm going to make this part equal to that part, and so on. So I have 1 plus 3 lambda, so that's the first x component, is equal to the second x component, negative 3 minus 2 mu. Make sure you copy this down nicely. You don't want to make mistakes in this part. And then minus 2 plus 2 lambda is 3 mu. And then we have lambda is 2 plus 4 mu. Now, you can take the first two equations, solve them simultaneously, but as you can see, the third one actually gives us a nice setup. So what I'm going to do is I'm going to take, so this is equation 1, 2, and 3, and I'm going to take equation 2 and 3 together. You could do 1 and 3 if you want to. You could also take the 2 plus 4 mu and substitute it in both equations and solve them all together at the same time. So there are different ways to approach this. You don't have to specifically use this method of approach. What we want to get to eventually is a contradiction at the end, is that we cannot find a lambda and a mu that satisfies all of them. So if you are approaching your question this way, and the algebra is correct and it's very clear, then it should be correct. So what I'm going to do, I'm just going to replace this 2, 4 mu into the second equation. So I have minus 2 plus 2, 2 plus 4 mu is equal to 3 mu. And I'll follow the algebra, and the algebra will get me to mu is equal to negative 2 over 5, which implies I'll also replace it for lambda. Lambda is 2 over 5. So I'm getting these two, and what I'm going to do is substitute in equation 1 and see does it fit in there. So I go 1 plus 3 lambda. This is going to give me 11 over 5. And then I have minus 3, minus 2, and it's going to give me negative 11 over 5. So I get we get a contradiction. So the lines do not intersect. So we prove they're not parallel. They do not intersect. Therefore, they are skew. All right, for the second question, we've done something slightly similar in a previous lesson, but where we proved 3 lines are concurrent. So concurrent means they meet at one point. So we're trying to find that single point of intersection, but this question is slightly different. We want the values of A and B such that the lines are concurrent, which means they have to fit, they have to intersect at a point. So we have to find a lambda and a mu that works for all of them. And what we're going to do is we're going to approach two equations, just like we did before. We're going to only take two lines here, sorry. We're going to take two lines. So I'm going to take L1 and L2 first. And we're going to follow the same process. You need to change these to vector form. So just like I did here, and then change them to this format. So I'm just going to immediately skip to this part. So we get to a 5 minus 4 lambda. The lambda is for L1 and the mu is for L2, just because I'm skipping some of the steps. 3 minus mu minus 1, 3 lambda, 6 minus 2 mu, and then 1, 2 lambda minus 1 plus 2 mu. So we have the setup here. And what I'm going to do is I'm going to take equation 2 and 3, and I'm just going to add them together, and it's going to give me a 5. So you're solving simultaneous equations here. 5 lambda. When I add these two together, the mu's cancel out and the negative 1 and 1 cancel out, so you end up with 5 lambda equals to 5. So lambda is equal to 1, which implies, if you substitute, that mu is equal to 2. So I have this, and let me check that they fit the first equation. So 5 minus 4 is equal to 1, and I have 3 minus 2 is equal to 1. So therefore they intersect. Okay, it's great, they intersect, but at what point do they intersect? By the way, we could start with the proving they're not parallel in this question as well. I'm just skipping to the part where we're trying to prove they intersect. So they intersect, but at what point? Once I find that point, then I could fit it into line 3, because I'm trying to make them concurrent here. So I have the lambda and mu. I can pick either. I'm just going to pick lambda because it's easier. I'll substitute it into my first equation, and that's going to give me the x, y, and z values. So you can substitute it here. What you do is you make this equal to lambda. Remember that all of these are equal to lambda, and then you solve it for x and so on for y and z. I like it in vector form because it gives me a nice easy calculation. So since I already have it in vector form, my lambda here is 1, and then when I solve it, it gives me 1, 2, and 3. So this is the point of intersection, and I want to fit it into line 3. So in line 3, I want to fit 1, 2, and 3. I want to find the A, B that would give me that. So 1, 2, and 3 should fit into, I'm just going to write it in vector form, plus there's a, let's say, gamma 1, B, and 4. So gamma is my scalar. So the first one, I'll have 2 unknowns, so I'm just going to ignore it. The second one, also 2 unknowns. I can see that the third one is going to give me a nice equation. This is 3. And at least I could find gamma from here. So the third equation is 3 equals to negative 5 plus gamma 4. And that gives me that gamma is equal to 2. Once I have gamma equal to 2, I can substitute it here. And so instead of gamma, I can now replace it with a 2, and I have a nice equation. So for the first one, I get 1 equals to minus a plus 2, which sorry, this is not minus a, this is just a. So this gives me that a is equal to -1. And then I do the same thing for b. I have 2 equals to 8 plus 2b. And that gives me that b is equal to -3. So in order for the 3 lines to be concurrent, these two do intersect, and they intersect at 1, 2, and 3. And for the third one to intersect them, the gamma has to be 2, and a has to be -1, and b has to be -3. If this is satisfied, then L3 will also have a point of intersection 1, 2, and 3 with the rest. Hopefully this was clear. You need to, it's a common question to see lines are parallel. Parallel is quite easy. That's why we focused on intersect and skewed lines as well.